This is group 58, lab 11. All right. So for this lab, basically I had to make a whole new different whole different lab. It's like one of those labs where you have to like design your own like elements. It's basically similar to lab 10, but you have to like design it yourself and find the same information, stuff like that. So learning goals, after completing this activity, you should be able to use the angular momentum principle to find the moment of inertia of an object under the influence of a non-constant torque. Design an experiment to find the moment of inertia of an object under the influence of a non-constant torque. All right. Yeah, this is like what I used. That's exactly what I actually used. I didn't use tape, but I got the IOKitLab ruler, robust axis, and pencil or skewer. So basically, like for this lab, you just find like a moment of inertia, right, through rotation. So what I did was I create a pendulum, and through that I just calculated forces for all of it. Like I got forces for the x and the z axis to calculate for moment of inertia. So question 1 says, based on the experiment in lab 10, come up with an initial design of an experiment performed to find the moment of inertia of the IOKitLab cart about an axis that is not crossing through its center of mass. So for this one, I created a pendulum using the IOKitLab kit and documented data from it to sort of allow us to calculate the moment of inertia of the IOLab cart around the x and z axis. Yeah, they said we can't use a ramp, so I just used what they were, the hint they gave us. Yeah. All right, first discussion question. Construct a scientific argument explicitly identifying all 3 components, claim evidence of reasoning that will convince other members on your team that the experiment design that you came up with Q1 is indeed the appropriate one to find the moment of inertia of the IOLab cart about the axis and not crossing the center of mass. All right, so my claim is what I said earlier. The evidence is basically like what Q3 is of all these questions. Like it'll show that like my experiment works, and reasoning is because of that as well. So basically the reason why it would work is because first, when we measure the angular acceleration of this pendulum, we would use angular acceleration formula, which is gravity times sine theta. And in this case, I found that it would just be 9.8 meters per second squared because sine theta equals to 1, and then gravity is 9.8. So that's how I got that. To find the mass of the IOLab cart, we just do it every single time, is you just basically use a force sensor, and then you just attach it, and then through that you're able to calculate your force, which is
Right.
basically your gravitational constant divided by your force, which is 4.9, right? Like found in this graph right here at the bottom. Like it just sways back and forth because it was on a pendulum. But yeah, like we always do it this way.
Mm-hmm.
Yeah, and then you just like, oh, I guess I didn't take a better picture, but you swing it up and down, like from this way to this way. So after that, you find the net external force of the IO card, which produces a torque. To find the torque of the IOLab, we use R radius, which is like your string, like this string right here. But we can do this by measuring the length of the string of the pendulum. Like this is like, it's asking what additional things you have to measure. And in this case, we had to measure more. The only thing you had to measure was the length or the radius of R. And through that, I found that the torque in this case was 2.3 Newton meters. Now find the moment of inertia of the IOLab cart experimentally. I found that it was approximately 0.3. Wait, is moment of inertia? What's the units? Is it Newton meters?
I don't think they have any units. I think all the units cancel for moments of inertia.
Okay, cool. And then using the calculated moment of inertia of the IOLab cart using theoretical formulas. The theoretical formula I use is torque equals the moment of inertia times angular acceleration. Since we found angular acceleration in part A and torque in part C, set them equal to do torque divided by angular acceleration, and that was around 0.234. Compare the experimental and theoretical values gotten. There's a difference about 0.06 between the calculated value and experimentally found results. So here are my graphs. Kind of messed up at the end, but you get the point.
Right.
Yeah, and then you get a little pendulum. So question 4, construct a scientific argument that will convince other members of based on your answers to Q, that you could find the moment of inertia of the IOLab cart on axis which is not crossing the center of mass. Wait, what does it say? I have no idea what it's saying. Wait, is it this exactly what we did before?
It seems like the same question as before, basically
Mhm.
just like that will convince other members your answer to Q3. You could find. Well, what's Q3 ask for?
It literally says construct, no? Construct a scientific argument.
What's question 3? Is it just like the things with the experiment?
I guess so. I guess it's a, yeah, I guess.
Oh, well then, yeah, you just use the experimental factors like the torque
Mhm.
and the acceleration and all that. And so you know that the net torque is going to be equal to like the change in angular momentum. And then if you can like figure out what its like angular speed is at any certain point, you can solve for the moment of inertia by like rearranging the equations that
Yeah.
involve those factors. So I think they're just trying to say like, how did you solve for the moment of inertia?
Oh, okay. All right.
'Cause,
Like the
like,
reasoning behind it. Yeah, that
yeah,
makes sense. I mean,
yeah,
yeah, all you do
which
is
you kind of
realistically,
already.
yeah, like just manipulate the equations to get your certain variables. I mean, realistically, the questions they listed on Q3, like telling the angular acceleration and finding moment of inertia, like you're basically given, and
Right.
you just find the formula
Like
for
it kind
torque.
of like feeds you into it. Yeah. So
Yeah, yeah. So I mean, it's pretty helpful. Discuss with other members of your team. What do you think are the reasons that the discrepancy? I mean, there's a lot of discrepancy, to be honest.
yeah, I feel like
Uh,
we've had like discrepancy with every lab. It's like
yeah, like,
the same things, right? Like force sensors aren't going to be perfect.
mhm,
Like the acceleration and all that's not going to be exactly right. And then
yeah,
we
like,
don't know if like the mass is uniform. Obviously, the string isn't massless,
mhm,
which in like all of the like theoretical problems we do in the homework and stuff, like everything attached to the object is usually massless. So it's like
Yeah.
yeah, and it's like
to get it
pretty,
perfectly, it would almost be wrong.
yeah, like I mean, there's like pretty small factors too, like wind resistance, yada yada yada. But
Yeah,
our
all that
it's
stuff.
not 0.06 isn't too bad. I mean, I think it's pretty
I mean, yeah,
reasonable.
that's definitely pretty solid.
Yeah, for sure, for sure. All right. Well,
Yeah,
I think that concludes lab 11.
relatively
Yeah.
short, pretty painless.
Or yeah,
Yeah.
I mean, it's exactly the last lap, to be honest.
Yeah, it kind of was.
I'm stop sharing.